All right. Thank you very much. So, yeah, thanks for the organization of this very nice conference and for the invitation today. It's great to be here. I'm going to talk about the separate cohomology of energy and about associated problems on graphic factors. And the structure of the talk is followed, and I'm going to start with something on background of the cohomology. Oh. One left basic purpose, which is E. And this is all going to be only about rational cohomology. Then I'm going to talk about the graph context group. And so in the third part, I'm going to talk about some results. And the results are going to be in order. This is also like a geometric talk. And I could have time. I'm also going to talk about modern basis of graphs. So I'm going to look at panorama of graph model space. Okay. So surely most of you know this, but I'm just trying to repeat some basic facts about this commodity of energy. And many of these results already have been on the blackboard during this conference. So, commodity and energy is supported in the range of 0 to A/(-5). And but the top commodity group benefits. So this is and this is the network. It's due to Jeff Butler and Morita Sakasai. Then there's a stable cohomology. So the cohomology of energy stabilizer. So I want to say this way to get a stable range. The best possible bounds are that's what I talk about. I know are that if 3K is smaller than equal to minus 2, then I guess exactly then the vector cohomology stabilizes with more stable cohomology infinity. And this stable cohomology is generated by the moduli and Miller class with the factor. So these are all topological classes. And these kappas, they live all in some one generator which easily Yeah, so I admit that I'm talking about commodity refractory coefficients in this talk because I'm only going to talk about cohomology refractory coefficients. Yeah, this is a famous theorem, but I'm not in advice. And this is just a notation. You can make sense of it by considering the co-limit, but this just will tell you that it is only the stable component. Okay. So there's also another result, an earlier result actually, on the order for instance. And we also have this already on the blackboard during the conference. So the order characteristic of MV, and to avoid confusion, I make it clear that it's so I mean the usual order characteristic. And this is just the evidence in some of the maximum. The coefficients here. So it's a result by Harald that as a topic, so they get an asymptotic formula for this one, and they show that for large G, it behaves like let's try the star, which people will use it. So this is the alternating sign, time star constant. And then there are two constants, the one and third constants times G, and this is taken to the power of 2G minus 3 over G. And this the tilde here is really line means that that the limit in both sides means that so the quotient in the limit to infinity is going to be more. The ratio of both sides approaches 1 for G solution. And so because the other characteristic is the alternating sum of the Betti number, it follows from this part that the dimension of the special numbers have to go at least like the absolute value here, this formula. And you can see that it goes super exponentially, so it goes from G to the power of 2. And also due to the sign, you also see that there must be many odd classes. So many classes must live in odd degree. And one of the questions, like on the topology of the smaller space, is where all this cohomology is coming from. And you can already see that the stable cohomology cannot be responsible for the odd classes because of the line size. Many classes in odd degree. So the question is, where is all the moduli? And yes, so there's something else. You can also be more pragmatic and say, okay, maybe the odd classes, they are not explained by the stable cohomology, but maybe even classes. But then you can just count, you can compute the dimension of these spaces, of these polynomial algebras. And this is something which is very easy to compute. So the dimension something pretty on the other with temperature only in even degree. We switch to the then this is just the number of partitions of the integer k. And this is like a very technical result into hardness maneuver that for large k, this grows like some constants to the power k square root of k. So this is a test. So the total dimension of the stable cohomology only grows like some constants to the square root of k, so it goes less than exponentially. And this growth rate of the color characteristic shows that the total cohomology grows super exponentially. So there's a huge discrepancy between the dimensions of the stable and the unstable cohomology. It follows from this that there's like lots of unstable cohomology. And the situation is a bit dire because at least before 2020, there were only 4 unstable classes known. And yeah, these were classes obtained by explicit computations of the polar cohomology ring, and the most example was back to Borinsky, who computed the cohomology ring for G equal to 4. Okay.
Sorry, but you get the cohomology only for some G from that distance. Right?
Yes. Yeah, only for even G, you get lots of cohomology. But even for odd G, this growth rate here is so large that it quickly dwarfs the amount of stable cohomology. And this also holds for the tautological classes, because also the tautological classes are bounded by these numbers because they are additional relations, but this is an upper bound of the amount of tautological classes. So we can also replace stable with tautological cohomology. That is, algebraic computation shows that there have been many non-tautological classes. So almost all of the cohomology is non-tautological. Only a very small part of the cohomology is tautological. So this should be right on the chain. And so frankly, it was a theorem that actually and they proved that something that I will define later. So the homology of some objects, it's going to be described objects, is isomorphic to the top weight homology of so I'm going to state it maybe in different language. So one thing that an injection of this object of this homology into the cohomology of energy. And they also set by the image of this injection, maybe this it lands in the it's anamorphic to the specific weight where the piece of the cohomology and in the top right it's so that's right going on. And for the experts, because we already had it on board, so this is actually a statement on compactly supported cohomology. So that what they actually did, that the zero weight graded piece of the compactly supported cohomology of and the it's computed is isomorphic to this HBC, which can be seen for so also as a brief explanation, because we also had it on the board already. So why is this so? How does it work? So it was in Sam's talk yesterday that we already saw the spectral sequence that's given by the direct sum of all stable graphs. Take down the tables and take the direct sum of all stable graphs below the stable graphs. Not then you take cohomology then gamma bar and gamma associated to the bounding components corresponding to the stable graph. And then depending on this with certain representation of the automorphism of the graph framework and take the variance like that one. And this is just an expression for the mean spectral sequence for this modular space in G. And now the trick is to just restrict to P equals 0. Take only 0. Zero dimension cohomology of this space. And in this case, this piece here is not going to be Q. And this whole row of the spectral sequence is going to be entirely combinatorial. So there's nothing going on here in these 10 gammas anymore. And that's a combinatorial complex. And this complex ends up being this commutative graph complex by consider. So there's only graph with this determinant representation. So now I'm going to explain how this complex of graph actually looks. In fact, there's also a complex of stable graph, but what I realized is that there's even a slightly more, and this is really only a slightly more efficient complex. And this more efficient complex, it turns out to have been studied by conceived and later by Böhmer. This complex intersection family. This is about which so this is a chain complex for an apparently great vector space. Vector space that's generated by pairs. So these pairs, they decide in called this data pair, this graph, and this terminant. So D is a graph, or is exactly there's multiple parts of the graph. And it's supposed to be connected, and it has rank D, that makes the first ranking about the graph equal to G. And then it's supposed to have vertex degree larger or equal to 3. And the sigma is just an ordering of the letters of this graph. I mean, this is the edges of the graph, and we want to number them, order them. So each graph comes with the numbering of its edges, and then we model out the relation. So we want to model the relation that for each permutation of these edges, X labels, the generator, and V sigma, V with the polluted X labels. We can pull out this permutation and just the sign of the permutation survives. So we will just give an orientation of the okay. So here's so I give an example, a non-example. And here's the non-example part of this graph. The 3 edges, you can number 1 to 3. But then we can use the relation and the exchange 2 of the numbers. But then these 2 graphs here are isomorphic, the same as what we have. So you just recover the original graph So the application was generated completely, but it's not a generator of the problem. More of a non-example. But yeah, so here's an example. On the part of the context. This one, and you can check that there are no morphologies that change this there are no morphologies of this graph that act as an even commutation on the set of references of this graph.
Are you allowing loops?
In principle, yeah. But they also will benefit from this. That is actually a statement of the bench. Actually, it's strong. They don't vanish because of the united, but they vanish because they are cohomologies. So there's a grading on the space, on the spectral space, obvious. Certain number of edges. The grading is the decay group, decay, UCD, are got the restriction to decay edges. And from these kind of restrictions, we see that the pores will decay with the pores in the range G to 3. So these are graphs that complete only on loops. And here is a pretty regular graph. So this comes from the graphs with only one vertex, and this restriction comes from graphs with the maximum number of vertices which are allowed with these rank and vertex degree restrictions, because we cannot build arbitrarily large graphs. And the differential is given by mapping one of these generators to the alternating from this, so the alternate with respect to this ordering, and each generator will contract with respect to the edge. And then we get a reduced ordering on this contracted graph in the long term. Ordering of the series useful to remove that.
So what you said earlier about the loops means that there's like a chain homotopy that removes a loop.
Yes. Yeah, I think it's already is this one. So these things this one, so you can just always blow up the move in this direction. Yeah. And also that the model is many times this graph is really for the fact and
But then if you have loops, the way you wrote, like it has to affect the loop, right? But it's
yeah.
So you
The rules are only into the one. when it's presented, so this is something which you get. This is the last part of the reduction from the stable graphs to these graphs, which have less information than stable graphs. But yeah, that's complex thing. Yeah, that's okay, so there's something known about this graph, okay? For this graph. Or what it is. There is- There's some property. There's also not so much anymore, right? This is only a target problem. It's pretty very complicated. To complete this. Someone to so, what is known is as a theorem by Goethe from 2015, and this theorem it first of all is dimension results, which shows that the 10% deviation in this graph context, when the commodity groups they vanish, if K is smaller than 2G. So this support range is not realized. Yeah, realized to a certain extent. Or K is smaller than 2G, this vanishes. And so this is one part of the theorem. And the second part is that in this bottommost commodity group, there's something interesting. We follow all the theorem. Then this 2D commodity instruction text. It actually carries the real algebra structure. And this real algebra is we talk about only tabular algebra. And as the name suggests, this only tabular real algebra has a very twisted personality. So I'd like to have a Jungian psychoanalytic one thing that is known the theorem by Brown about this group, and so this is actually using the theory of mixed-state motions. If there's a 3D algebra that injects into this only typing algebra. And so here starts this estimation of generator game again. So this 3D algebra is generated by odd rank generator. So each of these things lives in like so it's index that indicates the genome in which to use generator. And one can estimate like the dimension on such a 3D algebra. Only like fixed degree. Degree thing, and it's a simple calculation that this is actually going to this is some cost in power mechanics. So the dimension of such a 3D algebra grows exponentially with the degree. So there's one generator in each watch range. This is property. So there are exponentially many classes known in this graph homology due to this chain of arguments by river graph. And besides this, there are physical computations. And they go a bit further than for the modular space because the computations are not so they're ideal. So these computations are like panorama, random McKay, and also river. Okay, so this is results. And so if you remember the first part of the talk, there's a certain rhythm that I tried to put in here. So what's missing in the dimension of this graph homology is the order specific. Of this graph, of course. This the new theorem. So this order characteristic is again just imagining some of the second number of theorem. The theorem is like a formula, and that's a public formula for the side. And there are two different objectives. So this is for there's one constant. There's another fine. There's another constant. Times G. And what we call V minus C. For hot G, the antiphotic behavior is a bit more perfect. There's another constant. Then there's the function f of G. There's a second constant, which is taken to the power of square root G. Then there's a third constant, which multiplies with G, and taken to the power of V equals 2 minus 1. This is called out. And I didn't tell you what this function is. The function is actually we have an oscillator and we have to since the sine I over d and t over 2 technically the square root minus 4. Why is it likely? So this is pretty boring here, but this is interesting because this asymptotic behavior oscillate very widely because this variable of pi times g is rarely multiple of pi. So it's never a multiple of pi. But it's really close to a multiple of pi. And this is why I just yes. And so that kind of a funny thing. Exactly the phenomenon that the square root does never equal a multiple of pi, but it can get very close to a multiple of pi. And this is an issue if you want to use the same arguments as I did before to give like a lower bounds for the amount of cohomology. Amount of homology. But the fantastic thing about this function is that it's not any transcendental that pops up there. It's pi, which thankfully is like one of the most studied transcendental numbers. So they are very good bounds on the irrationality matter of pi. So people have concluded actually the irrationality matter of pi to a very good degree. Something that you of course don't have like any transformation. So for a generic transformation, I don't. But here we know like how close the square root of pi d can get to a multiple of pi. And we can use the to estimate what wins. So what can become smaller, this f of g, or with exactly so if we have like g very large, so we can make this f of g arbitrarily small, but for that g must become very large. And if g is very large, this factor the rho is also very large. So the question is what wins? Is it g to the power of g growth rate, or this f of g that can become very small? And thanks to these irrationality measures, you can actually show that the g to the power of g equates. This is a bit of a funny remark thing. So that the total theorem that is now printed into this each work is that so this is that the L characteristic magnitude of the L characteristic fulfills effectively the bounds that are suggested by this thing. So for G, where the constants such that so this constant times G to the power of G is a lower bound on the L characteristic, the magnitude of the lower L characteristic, and for us, there's a similar story. But the dominant terms is still this G to the power of 0 and 2. Okay, so. Yeah, this is only percent of cost always. It's all you have to make G appropriately larger. So there are finite linear sections to this inequality. So,
So can you give maybe an idea of how you improve?
yes. I might. So there's like a quick idea on the thing. Before I show you some pictures. So the proof strategy. So the strategy is that you change the graph context, then you form and commutative algebra of this you take all the units of this graph context and you put it together in like one commutative algebra. And then there's a trick. This is like a space that is generated by all possible graphs that fulfill the vertex degree restrictions that are possibly disconnected. So the connected algebra is where we can just multiply graphs and corresponds to disconnected graphs, and what can show that this thing is the same as the direct sum of a tensor product of two representations of this length. And these representations, they are actually pretty simple. So En is the representation that you get if you take the set of all participants of a set with n elements in which each block has size 2. This is the representation by a set of GAUS. Now there's an obvious and action on the set of machines where you just meet the original set of the set 1 to n. We can compute these integers, and that also gives an action on the set of seconds. And so we have an action. We want to twist this. We want to twist this action by the sign of the permutation it induces on this block. And this sign then produces exactly the sign that you need for this orientation. And this event is the representation that is being lost by substitutes, but the blocks are outside the same. But here the blocks are outside. And now all that is divided with 2. So this is true because we can think of the integers of 1 to n. It's kind of coefficient. We can write this anything below. It actually gives like a matching. This is the set partition which blocks of size 2. Then this Bn and write it slightly different. So there's a set partition which blocks over a larger B3. So we can just write the space and works. but also protect them. And if you remove both sides together, you get a graph. You calculate the selection, doing it together, it's a graph. And this is how you get this graph. And then it's like a technical exercise to evaluate the continuous character of these kind of representations. And if you do so, you can actually compute the dimension of the chain space. Just a sketch. And this is only one way to see it. So if you don't like representation, you just what's helpful with this evaluation of the direction, you get these community characteristics as directing functions in symmetric in the state of symmetric function. What's really helpful there is helpful to use passive methods. Sorry? Yeah, that's right.
I don't know, because one part of it is, I'll go back and have it come on.
Yeah, so this is only about the changes.
There's some
There's no-
connected thing.
Yeah, it's just making like all the graphs possibly disconnected. Yeah. So it's just this trick that enables you to apply have like some simple angle in this for say represent. That related technology also I mean, but I guess I'm not on them. But they can push the price of files, so they often need to kind of difficult. But they don't, they write them down, but they don't really use them and totally define them. So here you need to go a bit further and actually manipulate these things.
So what's the grading in this?
So the grading, yeah, so there's some technicalities going in here. So that's a very good question. So here, first of all, this is graded by the genus of the graph, but this is not the right grading that you want to use the trick. You want to change to the Euler characteristic of the graph, which is the same for connected graph, but for disconnected graph, it's something less than the genus. So we got the gradient here on this side, the Euler characteristic of these disconnected graphs, and the number of edges. It's bi-gradient. And here, yeah, this gradient is replaced, so you can replace this gradient to or you can relate this gradient to the number of these parts in this partition. The number of edges, and up here is the number of vertices. If you have control of the Euler characteristic, I still have time for some picture. Quickly. Oh, God. So here's a picture. Here's a picture of the cohomology of the G again from the beginning. So you see this blue wedge down there. This is the stable cohomology. And as I said in the beginning, there's like a sub-exponential bound on the amount of the cohomology. And this dotted line is the vanishing result by Putman or Morita Zakazaki. And this gray shaded area is like the area where there's lots of cohomology, but we don't know where it is. So due to the Euler characteristic computation, G to the power, it goes like D to the power 2D. So that this is the shadowy part of the cohomology. And there are these four classes known in the unstable range. The genus 4 part of the different. Here's the picture on the of the graph complex. So the blue area again, this kind of stability result by Wilbacher, but the pink line is the multipolar real result that looks on the diagram. And the pink dots are the vector space generator of this free real. So I mean they can become dense very quickly, and they actually grow like in exponential numbers. Exponentially many generators hiding behind these pink dots. And then these orange dots, they are a couple of explicit computations. And yeah, so the theorem tells us that here also in this pink wedge, there's like lots of homology hiding, and it goes like this power G. So now we can use the triangulation span result and connect this to the Euler effect of her homology. Then we see with this degree shift on the concave that's going on that this pink wedge maps like to the top of the diagram. So that's kind of a new stable kind of coming from the top. And this pink line where the one touching the other is right below the vanishing result by. And yes, it's scattered explicit computations. They also give classes in much higher degree and a much higher genus than previously. Actually, there's a typo there. So this 2D up there is supposed to be 4G minus 6. Sorry about that. So this is this pink diagonal just next to the one that is gives this exponentially growing line passes, and this the number of these passes goes much more to the same. And now the theorem mapped to this picture just shows that there are lots of cohomology with this pink wedge concentration. But you still see like in the different these scalings that the total cohomology goes like d to the power 2g. But in the picture, the theorem is just d to the power g or d to the power g over 2. So there's still much more stuff like hiding outside the wedge or inside the wedge, but like lower weight gradients. So it doesn't explain like the bike of the information stuff. So this theorem actually has triangulation space really explain this block range into a. And that's what I wanted to do.